Swirl exhaust ports help to jumpstart the next intake charge. And here's 3 examples. 2 valve per cylinder exhaust port on the left. And you'll see how the tangent side, which should be on the right in that picture, flows a whole lot more than the left side of that picture. I'm trying to get the exhaust coming out the tangent also. The center is where you have a 4 valve per cylinder engine, and both exhaust ports dump into a circle. Now, unlike the intake ports, we can't add epoxy in the exhaust. We could go in there and weld it up, but that's specialty equipment. It's not as easy as it sounds. So we have to find a way of creating a swirl and a bias with only removing material. But we want the velocity, we want to keep the ports small, so we have to be very judicious there. And then on the far right is a 16 valve engine where the ports come out side by side. Inside the combustion chamber, there's a lot of power to be made. This image shows a used cylinder head, and you can see the washed out area at the bottom there. Now, what's going to wash that out? A lot of liquids coming in that intake valve, for example. It could be a dead zone. I've seen the same engine with cylinder heads where that area is all coked in black, and the rest of the cylinder has a normal burn pattern. That zone is a dead zone on these heads. Now, the image on the right, you'll see that I put golf ball dimples in that dead zone. And it activates the boundary layer in the combustion chamber the same as a golf ball, activates the boundary layer to go further. You don't want sharp edges in the cylinder. So cylinder heads with a squish pad will typically have a sharp edge. And if you look at the picture on the left here, where the squish pad ends and transitions into the open area, lots and lots of sharp, abrupt edges. And you look at the image on the right, and it's all smoothed and radiused back. So we want to radius all the sharp edges in the combustion chamber. Why? Because if you took like a carton of milk, quart container of milk, square edges, and you hold a lit match behind it and you blow on it, it'll flicker. Blow harder. Blow harder. And you might be able to get that flame to go out. But then if you took something like a 1 liter bottle of soda, which is round, and you lit a match and put it behind there, and it's out. Very little effort. And this image shows how trying to go around sharp corners just doesn't work so well. But if you got a circle, the air will flow right around it nicely. Radiusing the combustion chamber helps what's called the Coanda effect. So the image on the right, you can see the water falling down on the very edge of the spoon, but instead of just falling straight down, it'll follow the curvature of that spoon. And if you're in the shower and you have water running down your arm, it'll hit your elbow and start rolling up and then fall off. Coanda effect. So radiusing the sharp edges in the combustion chamber allow the air-fuel charge to come in and swirl around with less obstruction. On the compression stroke, that swirling mix is going to act like a merry-go-round. If you're out at the very edge and you start pulling yourself into the center, the merry-go-round speeds up. So initially, when the piston starts coming up, you're going to get an accelerated effect until the frictional forces take over and then it starts slowing down again. Radiusing the combustion chamber reduce some of those frictional forces and allow it to keep spinning a little bit longer. And then when the spark plug goes off, that flame can walk right around that radiused edge and get back there to the back pockets. Whereas with the square, you're going to have a lot of combustion activity here, and in many cases, detonation going on back there. And the math, as far as how much total pressure is exerted on the piston, it would be pressure times surface area. And if all your pressure's in a little tiny pocket, total force on the piston is not much. But if you can spread that pressure out, now the total force on that piston just went up without changing anything, radiusing the combustion chambers. While you're in there, this image shows that on the exhaust valve side, we're going to take the combustion chamber open area right out to the cylinder wall. because as that piston's coming up, it's got to get around that valve and into the exhaust port. And by taking the combustion chamber out to the cylinder wall, it smoothly flows. If not, then it'll hit and you get that squared off effect. On the intake side, now it's coming in the other way, and leaving a little bit of a ledge there will create a little turbulence that'll help fling out some of the liquid droplets and make them smaller. There's the 95, 75, 55 rule, which states that 95% of the potential flow in a stock cylinder head, where the manifold bolts to the head, it flows at 95% of its potential. You can go in there and gasket match it, and you'll get, at best, another 5%. Now we move in that port a little bit, and we get to the choke point, as it's called. That's where it kind of goes from this direction to that direction. That's where your valve guide is. That's your choke point. Now, out of the box, the cylinder head typically flows about 75% of its potential. So spending a lot of time around the guide, you can get another 25% potential flow. And then 55% is where you're getting past the valve. That's the seat area. And that's where you can get the most benefit from a typical cylinder head as far as flow characteristics go. And again, here you can see on the left, that's stock as delivered out of the box. In this case, it's a 350 Chevy cylinder head. And then on the right, we cleaned up around the seat and around the guides. So we took the two most restrictive parts of the cylinder head, and that's where we spent our time. The seat itself, your typical factory seat will have like a 45-degree face on the intake valve, and for some reason it's like a 44-degree on the exhaust, but it's just a single face. So doing a 3-angle seat where you got your approach, your actual seat, and then a departure angle, 3 angles on the intake, as the air fuel comes in, the sharp brakes where the angles change will break that Coanda effect. So any liquids that might be trailing in there will flick off, and then it's just like your knuckle. You know, the water comes down, hits your knuckle, and falls. But if you smooth it out, it'll roll right around. On the exhaust, though, we're not flowing wet. A 5-angle seat or even a radius seat will improve the exhaust flow. Now, a 3-angle will work great and be actually more durable than a 5-angle because the seat surface is wider, so you're a little bit more durable with a 3-angle than a 5-angle. And then when you're done grinding and cutting, you're going to have all kinds of little tiny metal particles in all the oil passages and places you just don't want them. Now, okay, you want to clean up a power steering pump out back with the garden hose and some degreaser, but not the cylinder head. You really want to have the machine shop do the final tank on the cylinder head. But while you're in there, you're going to want the head resurfaced so that it's nice and flat to seal against the head gasket. You're going to want the guides checked and knurled or replaced as needed. And you're going to want your seats cut and your valves. So while the machine shop has it, just pay them to do that tank job. And of course, this is just trying to show some basic concepts, not so much show you how to do it. Head porting secrets, sub-tag is save gas and kick ... but is available on Amazon.com if you really want to get serious. Any questions on the cylinder head porting part? Yeah, modern cylinder heads are much better. It's the process that they used, 40, 50 years ago to actually cast the cylinder head and get it usable has come a long way. And so General Motors pioneered displacement casting where they use styrofoam that is exactly the shape they want. And then when they pour the aluminum in, well, it just melts the styrofoam. It comes out a vent hole as a vapor, and the sand is left exactly the shape they want. So the modern casting technologies have made it to where out of the box, a new cylinder head, there's not a whole lot you can do compared to, say, that old Chevy 350 head that I showed in the pictures. even textures. The GMLS engines have this little, looks like that thing that hangs in the back of your throat, right in the intake port. And so any liquids that are following down around the outer radius hit that, and they have nowhere to go except go right back into the velocity zone. There are really cool tricks that engineers have used on the more modern cylinder heads that just was impossible, for the older engines.